Thank you very much, and thank you to EDF and Amici della Terra for their kind invitation to be in this webinar. Oops, something went wrong with this slide. But yes, to introduce Kairos, we're a geospatial analytics company. We started looking at the energy value chain from the point of production to inventories all the way to demand. And but we've been very active these last 18 months looking at the end of the cycle, which is emissions and ending with the carbon sequestration. So you can see the slides again. So we don't do any hardware. We rely on external providers, including Copernicus, which has really given us a trove of really valuable data, and we keep finding ways of extracting more and more information from it. There are two ways we have implemented to track methane emissions using Copernicus. On the left, you see a map of Turkmenistan with a big number of orange dots. These are individual plumes of methane that are detected using Sentinel-5P. So these focus on methane hotspots, which are the big super emitters, is one way of looking at methane. And we believe, based on the data that we have, that this accounts for about 10% of total emissions from the energy sector. Then on the right, there's another approach using a full inversion model. So here we're using concentration levels to try to measure total emissions from an oil and gas basin or a coal basin. And again, comparing the output of those models with inventories, we believe this accounts for something in the order of 90% of total emissions. So much more comprehensive. Now, one of the benefits of Copernicus has been the transparency. Because we can now see events very soon after they happen, as is the case of maintenance work in gas pipeline networks. So here you see 3 recent headlines reported by the news based on our analysis and Copernicus data of events that in the past would have been unreported, maybe or maybe not included in company sustainability reports, but that now are out in the public, and we see them, again, gas pipeline network in Canada, coal mining in South Africa, and more recently, a very, very large release of natural gas from Gazprom's network, which appears to be some unscheduled maintenance due to technical malfunction. Now, one lesson so far to emphasize is, the contribution of the energy sector to these super emitters, which we put at around 80%. So a lot of it coming from oil and gas, but coal also being part of the story. And for us, this is a mitigation opportunity. These super emitters should not exist, and so a realistic but objective for the industry would be to eliminate all these super emitters in a relatively short period of time. This can be done. It would have a meaningful impact, and we have the information we need already today. We can also use Sentinel-2 for looking at methane, even though it was not intended to be a methane monitoring satellite. Here you can see a distribution of detections using Sentinel-2 and their flow rate. So, we know, again, super emitters are the very right-hand side of the tail end of the distribution. But nonetheless, we find events in pipelines and in oil and gas fields. And the good thing with Sentinel-2 is that we have a much better resolution for tracking down to the specific facility and operator that is responsible for it. And we have also a slightly lower detection threshold that varies between, half a ton to 2.5 tons based on the data we have so far. Now, of course, with time, we'll have more and more satellites. We're looking forward to Nmap. We're very much looking forward to MethaneSat because we know we'll be able to see more sources and have a lower threshold than is currently the case. But we can already do a lot with what we currently have. Another important point and lesson from all this Copernicus data is the importance of frequency. And here we have if we start with the right of this slide, EDF, who runs a lot of campaigns in Europe and the US, did a campaign where they picked up a large methane source over a compressor station in the Permian Basin. And they made 4 detections that we can see there between September 23rd and 25th. And because they made this data accessible, we noticed that, and we consulted the satellite data, and we were lucky. Both Sentinel-5P and Sentinel-2 were flying over that location on that day. So we could do measurements as well as with the third satellite, Landsat 8. So that's all very consistent. It aligns with EDF's measurements. But what we could see consulting the backlog of images from Copernicus is that we actually could see about 20 other measurements over that same facility in the previous 3 months. And so this is, again, one of the strong points of monitoring satellites. You have history, you have frequent measurements, and frequency is really essential for reporting emissions accurately and for verifying data reported by the operators. So we've been talking about hotspots. The other method is basin inversion. And this is, we think, very important to have an accurate and comprehensive view of total emissions from a region. So here you see monthly emissions in the Permian Basin with the 90% confidence interval, which is very much linked to the number of measurements that we can make using Sentinel-5P. So the more usable images, the narrower this interval will be. And to do this technique, we need to also understand what's happening on the ground. So on top, you see the actual average of concentrations from Sentinel-5P. And on the right is the reconstruction that takes into account which oil and gas companies are drilling where, and therefore where are the potential sources of methane that contribute to this overall amount of methane. Now it's interesting to see that the same approach can also work for coal mining. Here we're in Australia. The red squares are the location of large underground and open cast coal mines. And using that same approach of basin inversion, we're able to also measure the total footprint of these, Bowen Basin production area, and also to, estimate the footprint of individual mines or clusters of mines. And something we found that is quite sobering is that this coal-producing region, which supplies a lot of steel mills around the world, has the same carbon footprint as a mid-sized European country. So something to keep in mind in terms of scale. Now, another important point that we've learned using Copernicus data is the gap between top-down data and bottom-up estimates. On the top, you see the reported methane emissions of 5 oil and gas producers. So we looked at their sustainability reports. We converted to kilograms of methane per barrel of oil equivalent produced. And at the bottom, you see the average intensity of 3 large oil basins in the US. And what strikes us is the fact that there's a ratio in this case of 8:1. And it's something we see not just in the US, but more broadly, and also in the mining sector. Emissions reported based on emission factors tend to be much, much lower than the amount of methane we can see based on atmospheric measurements from space. So what this means is we need to reconcile the two, and that will involve, changing the reporting guidelines of companies, using all the technology we now have to measure emissions, and to close that gap, and the sooner the better. Now, methane, of course, also affects the entire value chain. So when you consider the associated emissions of gas in a power plant, Scope 3 emissions from methane on average can add about 40% to the Scope 1 emissions of CO2 from the combustion of gas. Doing similar analysis in the steel sector, based on that data I was showing about Australia, the increase in the total carbon footprint of a ton of steel produced goes up by about 24% once you include the methane content of the metallurgical coal that is being consumed. So just to give some orders of magnitude how methane data trickles down into the carbon footprint of various products that rely on fossil fuels. So to summarize, we have learned a lot using Copernicus data for the last 18 months or so. I'm sure we'll continue to find other ways to extract more information, and to improve the algorithms for processing that data. But the first point is, based on what we know already, there's already a lot that can be done to identify and make sure that we eliminate super emitters in the energy sector. We'll know more in the future, we'll have more tools, but based on what we know so far, there's already a lot of mitigation potential in the energy sector. Second, the frequency of observation is really key, and for the accuracy of reporting, for verifying that sources are indeed being taken care of. And third, and this is something that IMEO and others, I'm sure, will do a great deal to address, is the need to reconcile what we're observing from space versus what is being estimated using bottom-up estimates. So this gap that we see over and over again will have to be closed, and we think that's going to be one of the main focus areas for all the various stakeholders in the months and years ahead. So that is the end of my presentation. So thank you again for the invitation, and I'll hand it over to Steve.